moving on to our next keynote address of the morning. For those of you who are working in scientific machine learning, the next speaker needs no introduction. If you have ever tried to embed physical laws into a neural network, you are standing on the shoulders of his work. He's a pioneer in scientific computing and the leading figure behind physics-informed neural networks, or PINs. He is the Charles Pitts Robinson and John Palmer Barstow Professor of Applied Mathematics at Brown University. He leads major research efforts, including the DOE Center of Physics-Informed Machine Learning, and he is a recipient of the SIAM ACM Prize in Computational Science and Engineering. We are honored to have him here. Please welcome Professor George M. Karniadakis.
Great, thank you very much. Can you see my screen? Can you hear me?
Yes, sir. Yes, sir. Your screen is also visible.
Great, thank you very much for the introduction. I want to talk about a new topic today. 2025 has been the year of multi-agents, and this has also influenced scientific machine learning and computational science and engineering in general. So I want to tell you a virtual computational science lab. Of course, Athena was the Greek goddess of wisdom and reasoning, and this is why we chose that name. And as you will see here on the upper right, this framework is good for standard scientific computing, but also for scientific machine learning. So the outline of my talk, first I will say a little bit about scientific machine learning, some updates on the two pillars of scientific machine learning that were developed in my lab, basically PINs and neural operators. And then I will talk about agents and multi-agents, and I will draw a contrast as we go along. I have given talks before about PINs, and many talks about PINs and many talks about neural operators, so I will
recording in progress.
Here I will just simply show you some updates on what has happened lately on both fields. So just for those of you who are new in the field, scientific machine learning was introduced for first time at Brown University when I, with my colleague Jan Hesthaven, we organized this conference with the title Scientific Machine Learning in January 2019. And this is a picture from a screenshot from the homepage of the ICERM, is the National Science Foundation Mathematics Institute, where we had a sold-out event because this was the first time ever conference on scientific machine learning. So, as I said, the two pillars of scientific machine learning are PINs, neural operators. People, of course, would argue about other contributions, but I will only talk about our own contributions, my lab's contribution. And let me start by introducing what is a PIN. It's a physics-informed neural network. It's a standard neural network, as you can see here, where in addition to inputs, outputs, we extend the neural network to construct differential operators, because if we have differential operators, then we can enforce conservation laws, like, for example, here, the momentum equation for an elasticity problem. So then, in addition to mismatching the data, which is this term, we'll also have another term, which will be the mismatch in the physics. The fact that F1 and F2 which are the residuals of the conservation laws, have to be zero. Of course, the innovation that we introduced in 2017 in the paper, the first paper on PINs, was the fact that we did not need to have a grid to construct these differential operators, we simply introduce automatic differentiation, so all the differential operators are exact, and therefore you avoid artificial artifacts like artificial diffusion, artificial dissipation, which all classical numerical methods have. Instead, what you do, you compute the momentum equation or any conservation laws, you sample them randomly on a grid which consists of random points in space-time. And therefore, this method is not limited to low dimensions. In fact, we have demonstrated that pins can work in thousands of dimensions efficiently. Okay, so pins was very early on adopted by the industry, specifically Jensen Huang of NVIDIA in the Supercomputing Conference 2019. He introduced the physics-informed neural network. This is his words. And at that time, he hired my postdoc, Maja Raisi, who was the first employee in setting up the SIMNet and then what became the later Modulus, and today they call it NeMo, Physics NeMo. But this was all started from our lab based on Maja Raisi's innovations. Today, pins are used everywhere, in every sector, from black holes to molecular science to biomedical engineering and finance and so on. Of course, mechanics and geophysics, where there's a lot of data, but more recently, autonomous systems have produced a lot of good papers in that area. I'm not going to go to the details. As I said today, I want to talk about agents. So first attempt towards single agents was in this paper that we presented a comparative study for tasks in scientific computing as well as scientific machine learning. So a year ago, when DeepSeek R1 came out, we decided to benchmark it for scientific tasks, scientific computing tasks and scientific machine learning tasks against the competitors, ChatGPT, Claude, and so on. And so here's a list of all the LLMs that we tried at that time. And here is a specific example. We have many tasks in the paper, but I want to give you a flavor of a single agent. This is now a single agent that is asked to do the following. Use pins to solve the 2D Poisson equation in an L-shaped domain with zero boundary conditions and right-hand side equals 1, where the coding language is JAX. Okay, so the LLM has to write the code. It turns out that the code had a few bugs last year. This year it's better. And here I show you all the results from the different LLMs, from ChatGPT 4o at the time, ChatGPT Micro High, the DeepSeek V3, DeepSeek R1. This is Claude 3.7, and then the extended thinking. And you can see from all this, there are only two correct solutions. These are the two correct solutions, okay? We'll revisit this. This is a nice pedagogical example, but it does have some computational subtleties that one has to capture. Okay, so if you look at the table here, I'm not asking you to check all the table, but the various LLMs, these are again single agents, we call them. They use different points. They vary from 5,000 to 2,000, different architectures, different computational times and different activation functions, but you can see there are only two which have acceptable errors of the order of 5%, okay, for this problem. So that was the state of the art as of last year. However, pins and neural operators, as I'll show you, have advanced greatly since then. So pins 2.0, the version 2.0, for example, has new optimizers. And as you know, in neural networks, second-order optimizers are very, very important. So here we revisit one of the problems, namely the Berger's equation, the viscous Berger's equation, which we solved before. And if you look at the error versus the number of iterations, this is what we got in before, the green line in the top. Now with second-order optimizers, what we call the self-scale Broyden's method, which is like quasi-Newton method with a scaling factor, sort of precondition I will show you in a second, we get this result here. So we basically go down to 3 to 4 orders of magnitude, and we do that even faster by going to a second order optimizers. LBFGS that we use at the time, it is nominally a quasi-Newton method, but it doesn't achieve what these self-scale optimizers achieve, which is when you update the inverse Hessian, and you don't do that, of course, directly, you do it iteratively to avoid the order n cube complexity, we introduce the scaling factor here, which in a sense preconditions the Hessian. So the Hessian condition number, and we can track that, is always low compared to the standard methods, and therefore you can solve the optimization problem much more accurately and even faster. So there's this paper here, and we have other papers, but if you're interested in a paper to read carefully, this is one that we produced from my lab recently this year, optimizing the optimizer for physics-informed neural networks and also for CANs, for Kolmogorov-Arnold networks. And you can see, we compare here with SOAP. SOAP is the second-order method that Google introduced last summer. It's a pretty good method. It's basically preconditioning the Adam method. But you can see that these self-scale optimizers that we have beat Google by a huge amount, 2 orders of magnitude, for example, more than 2 orders of magnitude for the Burgess equation, an order of magnitude for the other ones, and sort of all the benchmarks. So these make a huge difference. There are other advances. People wrote here. I highlight a paper from University of Buffalo. Floating point 64 is all you need to avoid failures in physics-informed neural networks. It turns out that if indeed people were trying to, including our group, were trying to avoid double precision, but now using JAX, going to double precision, if you do it carefully, the computational cost only is 20% or 30% more than a single precision. So it's really worth going into it because you avoid the optimization getting stuck in local minima. So FP64 is important. Another important element when you're dealing with modern versions of pins is to use residual-based attention. That goes into the inside. This is not just the weights outside the global optimizers, but these are multipliers that go inside the loss functions for the boundary data, the constraints, the data, the observations, as well as the PD itself. So you put the attention where it matters, especially for multi-scale problems. This is important. Now we actually have a complete theory on how to justify these weights, the choice of the weights, depending on the norm that you normalize. Now, these high precision pins were discovered recently by DeepMind, and you may have seen the news that they basically try to solve, to discover singularities in the Navier-Stokes equations, which is one of the open problems announced with $1 million prize by the Clay Institute. So there was the only difference here is that they were using, as I said, high precision, double precision, and second order optimizers to get to this type of very high accuracy, 10 to the minus 16 double precision. Okay, so this is what I want to tell you about pins. I assume that some people or all of you know something about it. In 2019, we introduced a higher level of abstraction for various reasons, including the large energy consumption by neural networks. We introduced bio-inspired neural networks like the deep operator network, which we call DeepONet, which has some resemblance with the human neuron in the sense that we have different parts for an input. So we have an input that we call the branch, just like you have the branches here, to take the input in the human neuron. Then we have the soma, or the trunk, and here we have another that has to do with the output, where the calculation is done. And then the inputs, of course, for a neural operator are functions, and the outputs are functions. So unlike the standard neural networks, including pins, where the input space is data, finite dimensional space mapping to another finite dimensional space. In neural operators, the inputs are functions, the outputs are functions, and therefore what you have in between is an operator. Now, this operator doesn't have to be a differential operator, but it could be any black box. So in some sense, it's a system identification. It could be multiple operators. It could be a system of equations. It could be a simple equation, or it can be no equation at all. For example, in social systems, one can map inputs to outputs without knowing the governing equation, without having a differential operator. So this created a huge opportunity because in this new setting, you can do everything. You can train everything offline, and then online you don't need to retrain again. Therefore, no matter how hard the problem is, what is the dimensionality, how many equations, the output is obtained in real time in a matter of microseconds. So basically, you amortize all the cost as pre-processing. Okay, so we prove at that time the universal approximation theorem for operators for deep neural network. But basically, if you look at a shallow neural network, as I said, you have a trunk, which is has to do with the output, how you compute a basis for the operator, and then you have the input. So the input is u of x. You sample it or you project it, if you like, at certain points, and then that goes into the branch. And of course, if you have multiple inputs, you can have multi-branches, just like in a human neuron. I want to give you only one example, the simplest example we had in the original paper that appeared in Nature Machine Intelligence, which was the simple ODE, or you can write it as an indefinite integral, what we will call as antiderivative example. So given u of tau, which are some functions from a Gauss random field, given a certain correlation length, and then you want to map it to the indefinite integral s of x. Or if you look at the ODE, the corresponding ODE, you're giving the right-hand side u of x, and you're trying to find the operator d dx. Okay, so how do you train a system like that? Well, you train u of t the way we did it at the time. We took that DeepONet. We took 10,000 functions from a Gauss random field corresponding to a certain correlation length. We represent each function with 100 sensors, and then we computed s of x. That because here you have, say, it's a supervised learning, s of x only at one point. So we didn't have to compute although x is between 0 and 1, or if you do Laplace transform, it could be from 0 to infinity, for example. You don't have to compute it. Turns out that was the first finding we found, that this converges very fast. So we only need, for every function, we need only one evaluation. So if you plug in, you find that and you train it, the mean square error decays from 10 to the minus 4, 10 to the minus 5, and so on. And of course, this test is done for new functions which you have not used in the training. So that shows that it works and so on. So now I use this example because I want to go back to the LLM and ask LLM to a single LLM. It's a single LLM. It's a single agent. And I will contrast this later with multi-agents. So I want to implement a deep operator network in TensorFlow to learn the antiderivative operator, choose the appropriate architecture and hyperparameters for high accuracy and low computational cost, make sure that the model can generalize to a wide variety of functions. So here the LLM has to make some decisions. First of all, it has to decide a function space, has to choose a function space, which function space to choose functions u of tau, right? Because we map u of x to s of x. Well, DeepSeek R1 chose polynomials, it chose trigonometric functions, exponential functions, and so on. It didn't choose exponential functions. Gauss random fields. ChatGPT used 4.40 just choose polynomial functions. ChatGPT 03 mini high try something else. Claude is supposed to be more quantitative, use a Fourier series plus polynomials and so on. None of them actually use, and then Claude with extended thinking, an extra reasoning layer, use a mix of functions. It turns out in this example, DeepSeek-R1 is the best, and we test it against different correlation length. As you can see, as the correlation length goes to zero, goes smaller. Of course, you have high wave numbers, and therefore it's more difficult to resolve. So the error goes up, but it does a pretty good job compared to others. The others also give some reasonable errors, but Claude, for example, which is supposed to be quantitative, Claude 3.7 gives a very large error, and 3.7 with extended thinking gives a better error. So a year ago, this was kind of a mixed bag, right? You saw DeepSeek-R1 was the worst in the previous benchmark, but in this one with the neural operator seems to be the best. Of course, there are also advances in DeepNet. For example, we introduced, actually one of my former postdocs, who is now professor in North Carolina, Young John Shin, introduced a two-step training where instead of training together the branch net and the trunk net, since you have the label data, you can first take step one to train the trunk net and therefore the basis with respect to which you represent the operator, and then in step two, you train the branch and the DeepNet using a orthogonalized basis that you get out of the trunk. So that has this is what I describe basically here, is a two-step training. That has a tremendous effect, and we were able to, with using this new training, we're able to beat all other neural operators in the benchmarks, but also to solve very hard problems. For example, here we looked at Riemann O-nets, where we solve Riemann problems with huge, as you can see here, a huge ratio of the left state in the pressure and the right state. You cannot probably see the numbers, but it's a 10 billion. The jump in the pressure is 10 billion. 10 billion. So that's something that has not been done before. And we see stability, we see very sharp shocks compared to, for different initial conditions, okay? That's what is changing here is the size of the jump. So DeepNet can predict that, and the reason it can predict that is because it produces a basis, the trunk produces a basis which has all the features of the problem. So by fitting the trunk with the data, we can produce bases. For example, you can see the zero mode here. You can see the 10th mode of the basis. It looks like a Fourier series local, and then it looks like a wavelet away from that. The 120 mode, you can see that it looks like a Fourier series or a wavelet, but then it also preserves the constant state. So in other words, DeepNet, the modern version of DeepNet, produces bases which tailor exactly this the solution. So this is what happened. I wanted to give you a little bit of a flavor of some new advances, because going forward, the agents have to use these advances, which are now in the literature. And of course, all the LLMs have access to this literature now. So DeepNet provides a plurality of neural operators, can be replaced, the branch can be replaced by a graph neural network or even a spiking neural network, which is more bio-inspired, and the same thing for the trunk. So you can have lots of different manifestations. Now, the goal of the agentic scientific machine learning is to use multi-agents which collaborate. They can reason, they can generate new hypotheses, new solutions, and then they can refine continuously those solutions. They don't stay with the original solution, but by arguing and collaborating and reasoning, they can introduce new features which go beyond a human capacity. In fact, some of the results, or all the results that we get in one of our papers that I will introduce later, it's all superhuman performance using multi-agents. And I just show you that the single agent, the performance is it's certainly not comparable to human performance. Okay, so this agentic scientific machine learning has 3 steps. So let's look at step one, where the human provides a structure input. What does that mean? It means that there are prompts to give the problem, for example, solve the Navier-Stokes equations with pins, requirements, you can specify PyTorch or JAX or TensorFlow, and then evaluation metrics, use the PD and the boundary condition residual, and then you may, it's an optional to use data, your own data for training and your own data for validation, or it can generate its own data and then it has to check the accuracy. And this is now provided to the first agent, but also it's provided to all the downstream agents. In this example, I will use 10 agents. So the total number of agents in this framework will be 10. Athena, which I will introduce a little later, has many more agents. So now in step two, we have two agents, the data analyst and the evaluator. First, the data analyst is a multimodal analyst. What does that mean? It means that it can actually read plots. It can read XY plots. It can read column heat maps. It can inspect. It can produce correlations. It can make plots of correlations between data, so you can see if the data is correlated. It can look at the fidelity of the data, if there's noisy and so on. So that's the first pass of examination of the data. And then the evaluator will provide guidelines for evaluation criteria and metrics of accuracy, if speed is important and so on. But let's consider, for example, accuracy, that we want a small PD residual and a small data MSC. Okay, so step three, which I said there are 3 steps. Step 3 is now the main step, where we have the solution. So first, let's concentrate here on the top. We have an agent which is equivalent to the single agent that I talked about before. We call that a root solution because it's really the first guess. Okay, so this agent is able to produce a solution because it will follow the guidelines. It will execute and it will also evaluate the solution. Okay, now we're not stopping there because we actually want to evolve. This is really like a warm-up. It's sort of a predictor, if you like. Then now we want to evolve the solution and correct it. So first of all, we have here Mr. Knowledge. The knowledge retriever is the one who has read all the papers. So anybody who has questions can go back to this knowledge. It's basically a knowledge graph that we build based on papers specific to scientific machine learning that it has read. Maybe 30, 100, 200,000 papers. And then the main activity is done in this red box, where we have a proposer of an architecture, a proposer of a solution, a proposer of a transformation, but we also have a critic. And as you can see here, there is an interaction, there's a debate, there is reasoning back and forth. So they will go back and forth, they will start with the solution of the single agent, the root solution, but then they will try to advance it until we get an acceptable accuracy. So then we have the engineer and the debugger here will write the code, will debug the code, and will fix all the errors, but then we'll have an evaluator. All this will go back, as you can see in the blue arrow, will go back to a multimodal result analyst who will evaluate these. Okay, so that's how we close the loop. Now, as I said, there is an ensemble voting system to select the evolution directions. This is similar to what DeepMind has done recently with the AlphaEvolve. You may have seen something called AlphaEvolve that was in one of the papers that, in a mathematical paper that had 67 benchmarks. So they use the CAN benchmark, AlphaEvolve here. We develop our own. So we evolve the solution. We start with a root solution. We advance the best solution, and every iteration we will advance the best solution plus 3 other solutions. And you can see we use 3 different LLMs. We use Gemini 3.0, we use GPT, and we use Grok from Elon Musk. And each one has a vote, and so we always advance the best solution, but then there may be an initial solution that has a large error, but they see something that has potential because, for example, that solution may have large error because it was not given a chance to do a lot of iterations. So the same solution, if it was running for longer or changing a learning rate, it would have been better. So there's a potential. So we want to exploit and explore. We give them some freedom. And as I said, we have a diversity of GPTs because that brings, this diversity brings robustness and avoids hallucinations. So I'm going to give you several examples, basic examples to see how this whole system works. And you can also appreciate some of the ingenuity that comes in with these agents. Okay, so here's the first one is just a function approximation, not pins. Just so we want to approximate a function like this. The agent, of course, doesn't know the function itself, but it knows points. So we're given points from this function. So we give them points. So we ask to build any model of your choice for data regression using the provided database. So the database is after we sample this function. As you will see, this function is discontinuous, and it has also high oscillations. Okay, so we give some evaluations. We say use PyTorch and so on. So here's what the blue line here on the right is the exact function. The single agent, remember we have a single agent that finds a root solution, gives a root solution, which is this dash line, which is way off the exact function, as you can see. We chose the exact functions to have this spike, and then next to the spike we'll have high frequency to try to demonstrate the spectral bias for which all neural networks suffer from. So we want to see, okay, so the root agent chose a simple 5-layer MLP and only trained it for 100 epochs and got this dotted red line, okay? Now, there will be several iterations, as I said, between the critic and the proposer. And in the process, the champion solution, which is the final solution, it comes from multi-agents, has some surprises. For example, they propose a mix of expert architecture. That's a novel aspect. They propose a gating function, g of x. As you can see here, the g of x splits into two parts. E1 multiplies E1 and multiplies E2. What is E1 and E2? E1 and E2 are two different MLPs, so that one MLP will handle one part of the function and another one will handle another part of the function. In other words, the proposer and the critic agree into domain decomposition. This was not given to them. They decided to do it, and they introduce a gating function with unknown parameters k and x naught. What is x naught? X naught is where the discontinuity is, right here. And what is k? Well, k was inspired by the adaptive activation functions that we introduced years ago in this paper by my Indian postdoc, Ameya Jagtap, who is now professor at WPI, where we introduced adaptive activation functions. But here they took this gating function and introduced these parameters. In addition, they introduced an extra loss term in the loss function in the form of the entropy loss, because they wanted to have a clear separation between E1 and E2, the two neural networks which handle different domains. By doing that, they get a solution that has an error 10 to the minus 3 after 6 iterations. You can see actually how it evolves. It evolves from here. This is the root solution, and then eventually it refines it. So in this process of evolution, there are many things going on. There are many hypotheses. There are many different architectures. There's a neural architecture search. There's fine-tuning. There's, as I said, a mixture of expertise. And as you can see here, this is a list of all the agents which corresponds to different LLMs. They also have different temperature. Now, the temperature is a parameter that controls their temper or their creativity. For example, if their temperature is 0, then they're not very creative. They're very their actions are very sort of expected, deterministic. If the temperature is 1, they're very stochastic. So you can see here we gave 0.9 and 0.5 to the proposer and critic to make them creative. So the proposer will be very creative, will go beyond where humans have gone in this even simple example. The second example is something that that we did in earlier, Poisson equation on the L-shaped domain. So now, before we ask a single agent, now we ask this multi-agent, and we give some instructions, but minimalistic input. And again, we have this evolution. The architecture didn't change, but suddenly it did change, and then eventually, here's the root, and we want the score, and the voting here. There's a voting going this way. There's voting, which all these are solutions. Which solutions, and eventually the solution that we keep has error 10 to the minus 5. So that's pretty good error because remember we have this corner singularity. And how does it resolve the corner singularity? Here actually the agent did something that my students or my postdocs didn't do. Okay, what did it do? Well, it took the solution and decomposed it to a particular solution plus a neural network. And then we basically have to resolve the neural network more accurately. So that's innovation number one, sort of a transformation first, to break up the solution into two parts. Then it introduced adaptive sampling. So you can see here, put a lot of points, random points, but nevertheless, a lot of points around the corner. And now it's only the neural network, the non-particular solution that is done by a neural network. At the end, it has to add the two solutions. So here you can see that, remember, before we were getting errors 5%, now we get errors 10 to the minus 5. So the multi-agent beat the agents by a huge, huge factor, and I will summarize that later. Then I show you an example for a neural operator, namely the antiderivative operator. And now again, we ask for with very minimalistic input, we ask this multi-agent to do that. We generate the data, only the validation data. We don't generate the training data. We only generate validation data at 4 different correlation lengths. So we want to really test different wave numbers. So again, we start from an error, which is the best score is here. We improve the score. Small means better. And we get an accuracy for this problem 10 to the minus 3. Okay, so what was the innovation here? Well, the innovation was that the proposer agent reasoned that the integration operator is linear. And I wrote down this. Therefore, a successful neural operator said, should respect this property. So in other words, don't use activation function in the branch. So it chose a branch network which was a linear and a bias-free. It turns out what we did in our paper, we use nonlinear activation function for linear operator. Okay, in the trunk it used nonlinear activation functions. Another important decision that it made, if you look here at this histogram, and here's a length scale which has to do with the correlation length, it turns out that it sampled more the low correlation length, because the low correlation length corresponds to high wave numbers, and it tries to basically resolve the spectral bias of neural networks. So it's aware of the spectral bias, it's aware of the inability of neural networks to go to high frequencies, and therefore needs more data there. So it biases the low, the high wave numbers using that. So that's something again that the humans would not do. And you can see the results. We start with a solution which is 0.8% error, and we get to solutions which are 0.001% error. And of course, the lowest still has the largest error, but it's much lower than actually the length. There are some other novelties from other benchmarks we have. For example, for the Burgess equation, it introduced multi-scale features and self-adaptive pins using adaptive weights. Here, to solve the differential reaction equation using a operator network, he used an FNO with 4 channels for different coefficients, and then in addition, in the loss, he used a derivative loss term, kind of introducing Sobolev type training. And then also we had a benchmark for the flow reconstruction, where we use only 4, use only 4 sensors to reconstruct the vortex street, the von Karman street, very accurately. So it could basically do very diverse tasks. So what was the improvement? Here I have the improvement of multi-agent versus a single agent. For example, in terms of accuracy for the Burgers equation, it was over 10,000 times better than a single agent. For the functional approximation, it was almost 200 times better than for the Poisson L shape, 1,000 times faster, and then for the cylinder reconstruction, over 10 times better than the single agent. Okay, so what this tells you that there is actually discussion, there is reasoning, and this we capture that reasoning by monitoring the word count, how much these guys, how much these agents were talking. So, for example, you see the proposer here is the most talkative one. The second most talkative is the critic. Remember, I told you there's a pair of proposer and then the result analyst, of course, comes third, and then the data analyst guy comes at the end. They also have to vote. Everybody agrees on the number 1 solution, top 1, you can see. But then on top 2 solutions, mostly they agree. Here they disagree. And pretty much they disagree on the top 3, on the third solution. So, but they have to advance all of the solutions because you don't know which one will evolve to the best final solution. So this voting is very important, has to be done democratically, and that's what we ensure. I have a couple of more minutes, I think. And I want to introduce now a broader framework. That's the one that I started. Basically, what I told you so far is this scientific machine learning, agentic scientific machine learning. But we wanted to introduce this Athena, that stands for agentic, team, hierarchical, evolutionary, numerical algorithms, Athena. So this, as you can see, it's a whole virtual computational lab. There's only one user, that's one real human. Everybody else is an avatar. In fact, my student here selected to make, for example, this is me, the advisor here. This is one of my colleagues, Professor Maxi, who's a retired professor. He's working with me on fluid mechanics and various other. But all these avatars that you see are basically agents that do different things. So there's a big group or conceptualization group. Then here's the generative group. So you have a problem, you discuss the problem here, and then you decide, should I go with classical scientific computing, finite elements, finite different spectral methods that I like, or should we go with scientific machine learning, or should we store some of this data and we decide later, okay, if somebody gives you data. Then we have, of course, the implementation team that has access to the code retrieval team. Now, interestingly here, we give them some template codes. In the previous study that I show you, the agentic scientific machine learning, they didn't have any codes. They had to start from scratch. Here, that we give them some codes for, let's say, discontinuous Galerki methods, for the classical methods. Or we give them some finite difference codes. Then we also give them some pin codes or some neural operator codes. But so they will code and take in these codes and they change them and make them any way they like. So there's a very small library of these codes. So everybody has a very clear role here, from debugging to filing the data to growing the database and so on. And there's interactions at all level and also checking of the solutions. I'm only going to give you 2 highlights to see the superhuman performance that I talked about. I was very surprised, to tell you the truth. It's a little scary sitting there seeing that somebody else can do a better job than you. Okay, so the first question was, can you solve the implicit 2D Burgers equation? Okay, so I know how to do it, and I tell my students how to do it. Typically, we use a discontinuous Galerki method I know there's no exact solution. There's only exact solution for Viscus-Berger's equation with the Kohl-Hopf transform. But after some reasoning here from the Athena, decided that no, that Athena can find exact solutions for even this case. So it writes this equation in this form and says, well, if I do a transformation, if I do a rotation, I can have 1D. So I go in this direction, you see here, of propagation. So I rotate the whole reference frame, and I go in that direction, and then I can use the method of characteristics. So with the velocity v, which has components u comma v little v, okay, so I use the method of characteristics up to the point where there's a formation of the shock, and then separately after that. So I can find an exact solution. So in fact, you can see here Athena, which is the blue dot line, found an exact solution as opposed to Gemini and GPT and Claude, that they found different solutions, not the accurate solutions. So this is a decision just on the mathematics, right? He didn't do any pins, he didn't do any numerical methods. He decided to do a transformation, use method of characteristics, something that a PhD student would do, but they haven't done it. None of my students ever did that to find an exact solution on this, and I didn't think about it myself. Okay, and the last example, I want to show you the synergy between the classical scientific computing and scientific machine learning, and how the agents that want to reason and they want to find a good solution to this problem, how they cooperate. Okay, so what is the problem? The problem is you have the cavity flow. It's a fluid mechanics problem. You have a cavity flow, and you have, let's say, 500 measurements of only the u velocity. Can you, and there's also 5% noise from the measurements, okay? Can you reconstruct the whole flow field? Okay, we know that pins can do that, and in fact, the agents realize that, and they use scientific machine learning, they use pins to reconstruct here U and V with pins, okay? Now, they don't know the Reynolds number, but pins can also infer the Reynolds number. So based on the measurements and the Navier-Stokes equations, they found that the Reynolds number is 525. The correct one, it was actually 550, but they find 525. Okay, so they find 525. Now they go to say, let me check if this is actually correct. So they go, now that they know the Reynolds number 525 and they know the boundary conditions, they go to scientific computing and use finite elements, standard Galerkin finite elements, to solve the problem, the forward problem. Because if you know the Reynolds number, you know the boundary conditions, you can solve the forward problem. Before was the inverse problem, that's why they decided to use pins, because pins are very good for inverse problems. And then, if you do that, you see here they find a very good solution, right? It's smooth, it's very close to pins, but actually it's smooth. It filters out the noise and get very nice structures here, which is consistent with what we expect. And in fact, the error, if you look at the errors, then you look Q pins minus U, the one that comes from finite elements, the accuracy is pretty good, the errors are very small. So why I show you this example is because this was a synergistic cooperation of agents to use both scientific machine learning for the inverse problem, and then scientific computing that we trust for the forward problem, and then compare the two. And this is all done by agents. No human was involved. Everything was done on their own. They decide when to stop, they decide when to present these results to the human. So, in summary, what I have presented for first time, this is the first time I present these results, there are papers I can show you on the archive, but this is the first time that I give a presentation on this topic. An agentic scientific machine learning and a broader framework, Athena, that is basically a virtual computational lab for science and engineering. And in the traditional scientific machine learning, you have, let's say, a single model, but here in the agentic scientific machine learning, as you could see, the agents examine and employ multiple specialized architectures. In the classical approach, we have a fixed pipeline. Here we have a dynamic workflow with iterative loops, which is between the agents as they are arguing and in order to come to a consensus. Obviously, this is at this point is semi or fully autonomous. The error handling is different. I show you examples where the agent decided to, both in scientific computing and scientific machine learning, to do adaptive computations. The tool use limited tool integration in a classical approach, but in the agentic, you have agents that orchestrate all the solvers, they change the meshes, they can do uncertainty quantification, and so on and so forth. The exploration is much smaller using the classical approach, but using agents, they can explore really an infinite space, and they can do it really fast. Therefore, you can go beyond what human users, PhDs and so on, would do, or postdocs. So this is my talk. These are two references that you may find useful. The first one is the first part that I talked about, the collaborative multi-agent systems for emergent discovery in scientific machine learning. The second one is the Athena framework. And I also included the third one, which I didn't cover here today. It has to do with design, how you can use these agents to design airfoils. In fact, you can design airfoils better than humans or better than NASA engineers. And that's what this paper shows. Thank you very much. I just want to also acknowledge my sponsors, is the Air Force, and I hear some of my collaborators in a very large grant that I have, and also the Department of Energy. I'm a director of this CCROGS on a center. It's called Physics Informed Machine Intelligence. And thank you very much for your attention. Thanks for inviting me here.
Thank you, Professor Karniadakis, and in particular for staying even after crossing midnight. It shows your love for the subject and also the dedication. Thank you once again. And easily, of course, Professor Karniadakis could have easily said no, given the timeline is in, right? So it 12 past 45, right? Midnight. So
I'm happy, Shashi. I'm happy to answer questions.
Yes, thank you so much. Yeah, now let us take 2 or 3 questions. Yeah.
So I am Sudhir Biswas from IIT BHU. I have 2 questions. So the first question is, just to make sure I understood it right, you are using in the agentic SciML procedure, like the agents have multi-dimensional knowledge of various domains that is available over the internet. That's why they can implement domain-specific knowledges in the problem. Like in the first example, they used Boltzmann machines approach, where they introduce a temperature and entropy. In the second problem also they used adaptive sampling. So they have a broader range of domain-specific knowledge. That's why they can implement those things in the training as well. And my second question is, in the most of the cases in the scientific machine learning, we optimize functions, PDEs that are not eigenvalues problem. So there is only one value. But if we go for the eigenvalues problems, it splits into multiple orthogonal subspaces, and there are multiple values, multiple solutions. So in those kind of problems, how we can tackle and we can get to the solution? So that is these 2 questions.
Okay. Yeah. Thank you very much. So the first one was, you say they have specialized knowledge. I forgot to mention that here we actually did not train specifically the LLMs. These are the standard LLMs, the latest version of LLMs. But what we did is to assign them specific roles and boundaries and say, okay, you are supposed to do this, this, and that. So but we did not use Llama or any other things to give them extra knowledge for it. So they had to search it. There was also we have a knowledge graph which has some papers on the subject, but it's not even related to it. So it was a decision that was made based on the general knowledge that these LLMs have. Oh, okay. Now the second question, we actually published recently in the Proceedings of Royal Society a paper where we use pins to find multiple solutions of PDEs. In some case, there's like 10 solutions of PDEs, and we find them all. So pins are very good in finding multiple solutions, and it was a very, very simple observation that what you need to do is to change the seed, the initialization, to make, it's kind of like a deflation technique, but we do it through customizing the variance of the initialization by making larger and larger and larger, and you can find all possible solutions, because you basically, multiple solutions means that you have a local minima, and you can actually visit if you're careful. You can look at that paper. We have half a dozen of problems with multiple solutions. We get them all. So I don't know any classical DNS solvers who don't give you the global minimum. They will not give you multiple solutions. So because pins can do that, the agents could also do that, because they will do something like that. They will do a trick like that.
Okay, thank you. Next question. Yeah. Who's there with the mic?
Thank you for the insightful presentation. I am Arpan Nisu from the Department of Bioscience and Bioengineering, IIT Guwahati. My question is that how agentic SciML could be utilized for fully autonomous drug discovery, and which models would be better fit?
Sasha, can you please repeat the question, because there was some echo.
The question is like how the scientific or the agentic AI can be used for drug discovery.
Sorry, for what?
Drug discovery. Drug discovery.
We haven't done that yet, but actually I have one of my PhD students, Nazanin Ahmadi, who is working on pharmacokinetics, pharmacodynamics. He's working now with Carl Jung, the PhD student who wrote this first framework that they presented, to do something like that. But I want to also point to the paper that appeared in Nature. It's called the Virtual Lab, and the Virtual Lab by a professor from Stanford from chemistry and biochemistry. He was actually discovering some new drugs against the COVID variant. So this was one of the fundamental papers that inspired us to also work on scientific machine learning and make it agentic. But Virtual Lab, you can look at that paper. It's a phenomenal paper. They also did an experiment to demonstrate that the hypothesis that was promoted by the agents is the correct one. So they actually validated the hypothesis that generated by the agents using experiments in a wet lab. So I think, frankly, every area could benefit by this type of agentic framework. It is a matter of time before they mature, and also before we are able to train them. Let's say, imagine a case where you have these big agents, but also you have small agents, small transformers, that so you have a hybrid environment. So for smaller tasks, we can develop our own agents to do some specific jobs, and those will be specifically trained to replace me for my everyday jobs. Now we use these generalist agents, and they still do a very good job. But I think every area, including of course drug discovery, will be influenced by that, and we have already seen that.
Sure. Yeah. So let us move on to the next question.
Hello.
Yeah, please.
Hello. Sir, I am Ganesh Visram from IIT Kharagpur, and my question is it possible to develop this kind of agents or neural operators for multi-physics problems?
Yes. Here I didn't demonstrate that for multi-physics problems, but actually in the Athena paper you will see that we have several examples for multi-physics problems, including Rayleigh-Taylor instabilities and other difficult problems that include multi-physics, temperature, hydrodynamics, and yes. So there are many different ways of doing it. I have done some work before where we pre-train depot nets for each physics, and then you glue them together using data or using the multi-physics. But yes, it is possible to do that. I don't see any difficulty in that. It's just a matter of course, you have to have a supervisor that keeps track of the multi-physics, maybe interface conditions between and passing data left and right and so on. But yes, it's a matter of structuring right. There's no conceptual obstacle in this.
Maybe one more question.
Thanks.
One last question from the other side. Yeah. Could you please pass on the mic? Okay, it's difficult to move the camera.
From our experience of scientific computation, we know that these numerical methods face the problem of non-physical solutions or fictitious solutions. So do you also come across these kind of situations in this agentic approach?
So the question is, for example, in scientific computing, we get spurious oscillations and non-physical solutions. So the question is, did you observe such a type of scenarios in the agentic approach as well?
Yeah, so that was not in the case that I show you, but there's some Rayleigh-Taylor instabilities, which the accuracy was not good. There was either overdumping or extra oscillations, for example. And there was a critic, right? There's always a critic that goes with that before the advisor. So it goes back and basically they went back and they used a different metric for adaptivity. Instead of the density that you can, in compressible Navier-Stokes, they could use, for example, entropy as a metric, as an adaptivity indicator. So that was a decision that was made because of looking at oscillations. And then they did adaptivity using that. So that was totally on their own, decided to do that type of refinement. But as I said, these agents are now multimodal. They can see these oscillations, and they can go back and take action. So that's a very important. That's a new thing, actually. They go back and iterate 5, 10 times, 20 times.
Yeah, thank you.
Until they get it right. Yeah.
Yeah.
But you're raising a sort of very important point that you really need to have checks and balances, uncertainty quantification, and extra agents, because redundancy will bring you robustness. So obviously this is just a proof of concept at this point, but you will see in a year or two things will be much more mature as you will see.
Okay. Thank you. I know that there are a few more questions, but in the interest of time, right? So let's thank the Professor Karniadakis once again for their wonderful talk, and then in fact the very important, right? The first presentation of agentic scientific machine learning presentation. Of course, the CASML, we are blessed to have the presentation. Thank you so much, Professor Karniadakis, and we will be in stay.
Thank you very much for the invitation, and have a nice conference.